So today we're going to talk about graphing. So we just wrote down the equation for gravitational potential energy, negative G mm over R. And suppose we have some system of two objects, and we plot this function, gravitational potential energy, as a function of the separation, the distance between the objects. Okay, what should the graph look like? Okay, so we're pretty good. Okay, we're nearly unanimous that it's 1, which is correct. So we have the distance between the objects R. This is energy. And so we have, these are constants. R it's inversely proportional to R. So when R is small, the absolute value of this is big. When R is large, the absolute value is small, but there's that negative sign, which means that it does indeed look like this. And as we were just talking about, the gravitational potential energy due to the interaction between two objects really does approach zero as they get very, very, very far apart. So it needs to go to zero as they get far apart. So good. So some of you have had a chance to look at this in the context of an orbit, but so here's a VPython program that has a comet orbiting a star, maybe. Come on, run. There we go. Okay, so we've got a star and a comet going around it in a sort of elliptical orbit, which is what comets tend to do. And so if we calculate the gravitational potential energy every time we update the momentum and then plot it, we should get a plot that looks like this, right? So let's tell it to do that. So we'll say show gravitational potential energy. Okay, so it's plotting gravitational potential energy. So we've got this little dot moving on the graph showing the value of U. Is that making sense? So when it gets far away, it's approaching zero. When it gets closer, it gets more negative. So we're tracing out a piece of that curve. Right? Okay, so what should happen if we said, why don't you graph kinetic energy of the system 2? What should we see? Well, let's see how kinetic energies. Think about how the kinetic energy is going to change. So we want this one. Okay, so the comet's going away from the star. What's happening to its kinetic energy? And what's happening to its potential energy? Yes? I'm not talking about absolute values. Never. It's negative. That's cool. But remember that when a negative number decreases, it gets more negative, right? And when a negative number increases, it gets less negative. Yes. So the question is, thinking about not the absolute value. We're not talking about absolute values. We're talking about the actual value. Okay? So the comet, in this question, the comet is going away from the star. What's happening? Kinetic energy. What's happening to potential energy? Okay, so answer 3 says the kinetic energy decreases and the potential energy increases. So let's look at, is that what we were seeing? Did the potential energy actually, so as it was going away, as R got bigger, the gravitational potential energy got less negative, so it was increasing. And was the kinetic energy decreasing? Was it going, what would that mean? What would we see if the kinetic energy were decreasing? It'd be slowing down. So let's look and see if it's slowing down. Okay, so it's getting farther. Comet's getting farther from the star. And now there is an arrow for momentum, and it's unfortunately blue, so it's sort of hard to distinguish from the magenta, but it's getting big. Okay, so if we plot kinetic energy at every instant too, what should it look like? It's going to behave, opposite, isn't it? So let's tell it to plot kinetic energy. And, okay. So this is the gravitational potential energy. This must be the kinetic energy at this moment. Looks like when it's close to the star, it's going faster. It got more kinetic energy. When it's farther away, okay? So that's making some sense. Are they proportional to each other? Well, they're not really proportional to each other in the sense that here's the equation for gravitational potential energy. The kinetic energy, of course, is a half mv squared because it's not going near the speed of light. So they're not proportional, but if you're asking, are they related? Well, they do seem to be related, don't they? Because one increases, the other goes down. They sort of, it's like energy's flowing from the comet into gravitational potential energy, stretching the gravitational spring, and then back into kinetic energy again. So you've got energy flow within the system from kinetic to, so they're related in the sense of the energy principle, in that we've got E final is E initial plus work. We've already got it up here. And presumably in this system, there's nothing around to do work on it. We've got a simple isolated system here. So therefore, what should be true about the sum? Sum. Well, so if we have the final is initial plus work, and we pick the comet plus the sun as this. Yeah, it seems like work's going to be more or less zero in this system, and so in fact, what should be true of k plus u? Should be it should be constant, shouldn't it? So let's plot it. Let's plot the sum. So that looks like the gravitational potential energy. That's the kinetic energy. This is the sum, k plus u. Is it okay that it's a negative number? Apparently. Is the real total energy of the comet-sun system negative? What's positive? Rest energies. So they've got these huge positive rest energies, which if we tried to plot them on this scale, they would completely dominate and we wouldn't even really be able to see these curves. So, and that's not changing. So they've got this huge positive rest energy, but negative gravitational potential energy. So let's think about, and so as you predicted, the sum of the kinetic energy and the gravitational potential energy is a constant, which is, I think, the relationship you were looking for. Energy is flowing back and forth from one to the other, but the sum is staying constant. So let's think about what kinds of graphs we might see of k plus u. So what we saw here for this particular system was this was the gravitational potential energy. The kinetic energy, could kinetic energy ever be negative? No. No. Okay, so it was positive, and it did something like this, and we had the sum. We need another color, green. The sum was actually, in fact, we weren't looking at this whole graph, were we? Because it never really got that far away. So we were kind of looking at some piece of a graph like that, and we had k plus u kind of like that. So what else could it look like? Let's think about it. So could we ever have a situation where the graph kind of looked like that? Yeah, maybe. Maybe. Could we ever have a situation where the graph looked like this? Yeah, in principle, all those things are possible. So let's just think a little bit about what the meaning of that actually is. Let's actually just look at one question to just make sure we're clear on adding graphs. Here's some graphs of a graph of kinetic energy for some, not this system necessarily, some system. Kinetic energy, gravitational potential energy, and the sum. Which one correctly shows the sum? That's the cyan line there. We're just adding graphs here. We're just making sure that we're just doing a little math here. We'll talk about what the system is in a minute. Ooh. Okay, well, I'm glad we did this little exercise. Let's talk about heuristics for adding graphs. So the thing to do when you're asked to add two curves is to find one or two places where it's easy to do. And one place it's easy to do is where one of them is 0, because 0 plus something is then that something. So the first thing we do is we say, well, here's the potential energy curve, and here it's nearly 0. So the sum at that location would need to be 0 plus k, which it would need to be k, wouldn't it? And so this is the only straight line we could draw here where at this easy to add place k comes out to be the sum of, okay? So look for some easy place, easy point to add it. So let's think about what this would mean, though. We saw that, so we've seen a couple different situations. We saw this for our comet orbiting the star. We had kinetic energy, and we had the sum, which I think we decided was green. The sum was actually negative, so k plus u was negative. And it never got infinitely away, right? It had a farthest distance it could go. So this was Comet plus a star. Now the problem we did at the beginning, where we used the momentum principle to find the speed of a satellite, and then we calculated the work done, the minimum amount of work you need to do to move the satellite really, 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 really far away from the Earth, so it's not moving at all. And so we remember the equation we had? We had the initial, the final K plus U ended up being what? 0, because it had 0 kinetic energy and the gravitational potential energy was essentially 0. So we ended up in that system in a situation where gravitational potential energy went to 0, kinetic energy went to 0, and so in fact the sum of K plus U, this is K and that's U, that was 0, and this is where it does manage to get infinitely far away, but K equals 0. So this is referred to as escape, where it actually manages to get infinitely far away. So it's not going to come back in this. Okay, it's managed to get infinitely far away. So this is as far as it gets here. This is K plus U, and it's negative. What would the graph look like if the satellite or the comet, whatever it was, managed to get infinitely far away, but it wasn't at rest? It was still had some energy, so it was still had kinetic energy. It was still moving. Yeah, okay, so kinetic energy never gets to 0, so kinetic energy is going to look like that. And so that's the problem we just did, right? K plus U is going to be the sum of those two, so K, and this is U. So this is escape also, but it's escape with some extra energy. So this also escapes. So it looks like in a situation where the sum of K plus U is greater than or equal to 0, the system, the moving object can get all the way away, it can escape. Whereas when K plus U is less than 0, it can't. So we call this a bound state, K plus U less than 0. And we call these two states unbound, or sometimes free, if K plus U is greater than or equal to 0. And so for systems that are bound together, like the Earth and the Sun, or your little satellite in your program and the Earth, unless you give it a lot of initial kinetic energy, K plus U, it's going to be a bound state. K plus U is going to be negative. But if it has enough energy to escape, K plus U is greater than or equal to 0. Questions? All right. Gravitational potential energy near the Earth's surface. We actually worked this out at the very beginning, and we discovered that, so we sort of had the change in potential energy near the Earth's surface. Remember, we were dropping a ball on the first day we started talking about potential energy, and that ended up looking like mg delta y, which doesn't look like that at all. But of course, it's the same reasoning we went through for the gravitational force near the surface of the Earth. We could calculate it this way, but the change in R is going to be awfully small, and so we don't have quite enough significant figures. So really, the gravitational energy of an object near the Earth is actually equal to mg y plus some large negative constant, g times the mass of the Earth times the mass of the object over the radius of the Earth. But since this is never going to, in order to avoid just writing this large negative constant all the time, we often just leave it out. But it's really what it actually is. Okay. Question? Yes. Well, what really is okay, so what actually is the gravitational potential energy of an object sitting on the surface of the Earth? Here's the Earth. Here's the ball sitting on the surface of the Earth. So the distance is the radius of the Earth. So at this moment, the gravitational potential energy must be negative g, mass of the Earth, mass of the ball, over the radius of the Earth, right? Now we want to get the potential energy of the system when we pick the ball up 1 meter. We lift it 1 meter off the surface of the Earth, okay? So, well, we know the change in the gravitational energy is going to be the work done by me, and it's going to be an mg change in y. And so now the energy is going to be, final energy is going to be a minus g, mass of the Earth, mass of the ball over radius of the Earth, plus an mg delta y. But this is just annoying, so we usually kind of leave it out and we just say, well, it's 0 here and it's mgy there. Okay? But the point I really want to make is that it's not that they're two completely different kinds of gravitational potential energy, that even if we're using this mg delta y to calculate changes of something near the surface of the Earth, it's really the same thing. It's not a completely different thing. So thank you.